All right, hello. Welcome to this week's Math 2414 weekly review. This week we'll be covering section 11.8, which is power series, as well as 11.9, which is representations of functions as power series. So just before we start, this week will actually be our last week of having weekly reviews, and we are working on trying to get a final exam review, so just be on the lookout for that. All right, so now let's go ahead and begin with power series. All right, so a power series has a very specific representation. It will look like this. You will have your summation from n goes to 0 to infinity of some c to the n times an x to the n. So this x to the n right here is going to be the really important part of your power series. And of course, when we expand this out, we can see it'll look something like this, where we'll get c sub 0 plus c1x plus c2x squared plus c3x cubed, and so on and so forth. So whenever we talk about, whenever we have these power series, we can see how we have a bunch of different pieces in here. So what we're going to do is we actually go ahead and refer to x as our variable. So we don't know what x is for sure in any given stance. That's something we have to figure out. And then we have that cn, and that is what is referred to as our coefficient. So that coefficient is just any other part of our function in the power series. It could be a constant, but it doesn't have to be a constant. It can just be anything, any constant or anything in terms of n. We just know that it is not part of that power series. So whenever we talk about power series, whenever we think, we can talk about a little bit about convergence and divergence. So like we said, x is an unknown variable. And because of that, convergence and divergence depend on x. And this is actually kind of a little based on geometric series. This is just kind of a more general form of a geometric. Think about this as kind of a general form of a geometric series. So that's kind of where we can get the idea. So remember, in geometric series, our ratio, like r to the n, whether or not it converged or diverged depended on what r is. And this is kind of the same thing. It depends on x. So before we move in, let's move down. There's also a couple other forms where you could see this. But of course, they're all kind of just the same basic idea. You can get a form that is a little more simplified, to where you can just have, and it goes from 0 to infinity of just x to the n. That is going to be pretty much your most basic form that you can see of this. Because like we said earlier, that x to the n is really going to be the important part of your power series. But we can actually go ahead and expand this a little further, to where we can have n goes from 0 to infinity of c to the n times x minus a to the n. We can see that we still have our x to the n in the same way. It's just essentially we just kind of shifted it over. And whenever we have this, we actually specifically call this a power series centered at a. So now that we've kind of gotten a little bit of that out of the way, let's go ahead and move on to our first theorem for today. All right, so we have a theorem that states for a power series, and we usually just put it in our center to A form just because that's our most complex form. There are three possibilities. All right, so our first possibility is that our series will converge only when x is equal to a. So essentially whenever we have a 0 like in here, when we get like a 0 to the n in there. Then our next possibility is that our power series could converge for all values of a. So infinity to infinity, no matter where you plug, what you plug in, it will converge. And lastly, and the last scenario is where there is a positive number r such that the series converges if x minus a is less than r, or the absolute value does, and diverges if x minus a is greater than r. So essentially what this is saying is that essentially we have like a limited interval to where we can go ahead and have this and essentially have our series converge. So whenever we're talking about this, we consider r to be what is called the radius of convergence. So essentially what the radius of convergence states is how far away from A can you get for your series to still converge. And then we also have what is called our interval of convergence. And that is essentially saying like what are all the values where the series converges. And this, once again, is pretty much just like a mix of a geometric and ratio test. So I believe whenever we covered ratio tests, I think there may have been a homework problem on there where they essentially said find where this is convergent. And this is essentially kind of the same thing that y'all did back then. So we can actually go ahead and do some examples on this. So we're going to do a few of these. For all of them, it's just going to be find the radius and interval of convergence. So for the first one, we are given the series x to the n over n factorial. All right. So in order to do this, usually the easiest way is to go ahead and actually compare our power essentially plug our power series into a ratio test and then solve for x. So let's go ahead and start off with just mainly because we know with our ratio test that essentially, number one, it gives us our absolute value, so it's easy to compare, and also that gives us a definitive line of this is convergent and this is not convergent. So that's typically why we use our ratio test. So of course, our ratio test, as a quick reminder, is our limit as n approaches infinity of the absolute value of an plus 1 over a sub n, and it is convergent when that is less than 1. And of course, if it's greater than 1, if it's greater than 1, it is divergent. If it equals 1, we have to try something else. All right, so let's go ahead and work with this. We have our an plus 1, so we can get x to the n plus 1 over n plus 1 factorial. And we're going to divide by a sub n, or we can also just multiply times 1 over a sub n. So we can just multiply times n factorial over x to the n. So our first thing we need to do here is go ahead and clean this up a little bit. So we can go ahead and say we have x to the n times x to the 1 over n plus 1 times n factorial times n factorial over x to the n. When we do this, we can go ahead and cancel some of this out. So now we are left with x over n plus 1. So now we can go ahead and plug in our limit. Limit as n approaches infinity of x over n plus 1 is less than 1. Now, typically when we do this, we plug in like any grouping of x just to make it easier to find our limit. So we can go ahead and pull out our absolute value of x. So if we take our limit absolute value of x over times 1 over n plus 1 as n goes to infinity, we're essentially going to get x over infinity. So this is essentially going to go to 0, this limit. And we know that's, of course, going to be less than 1. And this is always going to be 0 no matter what we put in for x. Since, of course, x is just going to be any constant number. So therefore, we can go ahead and say that our radius of convergence is infinity, and our interval is equal to negative infinity to infinity. All right, so let's go ahead and try another one. All right, so in this one, so in this one we have our series, n goes from 0 to infinity of x minus 2 to the n over n squared plus 1. So once again on here, we're going to go ahead and start off by using our ratio test. So what we can do is we can say that we have x minus 2 to the n plus 1 over n plus 1 squared plus 1 times n squared plus 1 over x minus 2 to the n. All right, so next up, of course, is going to be clean this up a little bit. So we can go ahead and get x minus 2 to the n times x minus 2 over, if we expand out that n plus 1 squared, we're going to get n squared plus 2n, and then plus 1 plus another 1 plus that other 1. So we can go ahead and just do a plus 2 for right now, times n squared plus 1 over x minus 2 to the n. All right, so now we can go ahead and cancel some stuff out. So it looks like really the only thing we have is this x minus 2 to the n. All right, so now we have so now we can take our limit as n approaches infinity. We can go ahead, let's go and pull out our x minus 2 and leave that in our absolute value. And then we can find our limit of n squared plus 1 over n squared plus 2n plus 2. All right, and then we need that to go ahead and be, and we're going to set that inequality equal to less than 1. So if we go ahead and solve for the limit of just this piece, of course, we're going to go ahead and get 1. And just by looking at it, we can see it's going to be 1. So therefore, we can say that we have the limit as n approaches infinity of, or wait, actually, we don't even need that limit anymore. We can just, since we already found it, we can say that x minus 2 has to be less than 1. So now we have the absolute value over there. So what we can actually do is we can go, to get rid of that, to solve for this inequality, what we can do is we can say that negative 1 is less than or equal to x minus 2, which is less than or equal to 1. So essentially we just put a negative out in front of this number right here in order to get rid of that absolute value. If we solve for both sides over here, we get negative 1 plus 2 is less than x, so therefore we can get 1 is less than x. And then if we look over here, we can see that we have x minus 2 is less than 1. If we solve for x, we can get x is less than 3. So therefore, we can say that we have 1 is less than or equal to x, which is less than or equal to 3. All right, so let's go ahead and look at this right now. Now we can go and look at our radius and our interval. So if we look at our radius, actually your radius will actually, you can find it using this step right here, and it'll just be whatever number you have over here on the opposite side of your absolute value. Just make sure that you just have like x minus a, make sure you don't have anything else over there. You can just have absolute value of x minus a, that is it. Like don't divide or multiply by any constants. Make sure those get moved to the other side of the inequality first. All right, so from here we can for sure say that our radius is equal to 1. But now we also have to look at our interval. So whenever we do our interval, we don't know for sure whether or not that we will converge or diverge at our endpoints. So whenever we get to this point, we have to go back and plug in our endpoints into the original series and then solve that and see if it's convergent or divergent. So what we can do is we can now go ahead and plug those in and say for our first endpoint that we have, we get 1 minus 2 to the n over n squared plus 1. And of course, that one will get us negative 1 to the n over n squared plus 1. Looking at this one, we can do alternating series. And by looking, and if we just look at it, we have a constant on top, n squared, and the denominator of our limit will go to 0. And we can also look at it and see that it should be decreasing. So therefore, it will converge through our alternating series test. So now we can go ahead and look at our other one. So now we can go ahead and plug in 3 to get us 3 minus 2 to the n over n squared plus 1. Well, that's going to get us 1 to the n. However, 1 to the n is just 1, so we don't really even have to worry about that, putting that n up there, over n squared plus 1. All right, and then just looking at this one right here, we can essentially kind of use like a pseudo p-series. We're not going to actually do the work on it, but just know that like we can use a p-series test. Maybe you have to even do a little bit of comparison tests to see that this one will also converge. And because each of these converge whenever we do our interval, so let me go ahead and let me actually go ahead and just rewrite our radius down here. Radius is 1. Our interval will be closed bracket 1 to 3 closed bracket. If one of these diverge, so let's say for example if 3 diverged, then you would write an open bracket anywhere it would diverge. So like for example, it'd be like bracket 1, 3 parentheses. So just make sure to keep track of like how you write your interval notation whenever you get to your exam, whenever you do this. All right, so I just have one more example for this section, and then we'll go ahead and move on. So this one we have another series. In this one we have n factorial times 2x minus 1 to the n. All right, so once again, we can go ahead and start off by using our ratio test. So we can go ahead and plug in our n plus 1 in for everything to get n plus 1 factorial times 2x minus 1 to the n plus 1 over, and then over our initial, so n factorial times 2x minus 1 to the n. All right, so now we can go ahead and clean this up a little bit. We can go ahead and get n plus 1, n factorial, 2x minus 1 to the n times 2x minus 1 over n factorial times 2x minus 1 to the n. That's an n. I don't know why I wrote a 2 there. All right, go ahead and cancel out. All right, so now we are left with our limit. As n approaches infinity, we can go ahead and put our absolute value around our 2x minus 1 and times our n plus 1. So just looking at this, that limit as n approaches infinity of n plus 1 will always be infinity, which we know, of course, is greater than 1. So therefore, we can say, and because that will always diverge, we can say that we now have a radius of 0, because we can't really get that, because there's going to be no really way to get that. Modify this to get it to converge. But remember, if we go back up to our theorem, it says that it will have to, at minimum, converge at x equals a. So therefore, we can say for our interval, we can solve for a down here. Of course, 2x minus 1 is equal to 0. 2x is equal to 1. X is 1/2. So of course, right there, we can then say that our interval can be, you can either say x is 1/2, or depending on how they want it, you can just say 1/2 to 1/2. I don't know if your profs have a preferred way of how you put that in, but that's how you go ahead. But you will but like I said, at the very least, you will have it at x equals a, or wherever you can get that little inside part to go to 0. All right, so now let's go ahead and move on to section 11.9, and this one is going to be representations of functions as power series. So whenever we do this, we have one base idea that everything's going to connect to. We can say that 1 over 1 minus x. Of course, if we expand that out, we could do 1 plus x squared plus x cubed, and it'll end up looking like that. And we can say, of course, that that is equal to our summation as n goes to 0 of x sub n of x to the n. And of course, the absolute value has to be less than 1 for it to converge. So this is pretty much actually based off another one that's kind of based off of geometric series. However, since we're going to talk about representations of functions, we can see how we started off right here with a function and ended up with a power series. Well, we're going to have to end up using this format for pretty much any function that we have. So let me go ahead and do some examples so I can show you like what I really mean by that. So I'm going to do a few examples. All of these we just want to find our power series representation. So for our first one, we have f of x is equal to 1 plus x. So like we said earlier, we know that 1 over 1 minus x is equal to x to the n. So what we want to do is we need to go ahead and manipulate this function right here to get us something in a similar format to our given function. So what we can do is we can take this function right here and say that this is equal to 1 over 1 minus negative x. So now we have our 1 on the top, a 1, and then a 1 minus some sort of function in the bottom. So now what we're going to do is we can take this piece, now we're in our right format, we can take this piece right here and plug it in for x. So therefore we can take this and say that this is equal to the series of n goes from 0 to infinity of negative x to the n. And from here, if you want to take it one step further, you could even say n goes from 0 to infinity and split up that negative 1 in the x. And this would be your final answer. So yeah, essentially we want to get 1 over 1 minus something. And then that's whatever that something is we substitute that back into our initial idea of our power function. So now let's try one that's a little more complex. That way you can this one's kind of hard to teach without showing examples of how it works. So like you'll kind of see more just as I do more examples. This one we have our function is equal to 2 over 3 minus x. And of course, I'm just going to write our main one up here. All right, so we can see we still have a minus x, but now we have a 2 and a 3 in there. So first thing we're going to have to do is we have to figure out how to get rid of those. So what we can do is we can take this 2 and factor it out and say that we have 2 times 1 over 3 minus x. Now we have our numerator, it looks fine. Now we have to worry about our denominator because now we have a 3 minus x. We really want a 1 minus something, some sort of x. So what we can do now is in our denominator, we can go ahead and factor out a 3 from there. So 1 over 3 times 1 minus x over 3. So we can say we have 2/3 times 1 over 1 minus x over 3. So now we can take this piece right here and plug and use this to plug straight into the power series and then use our 2/3 to multiply. So where we can get our series is n goes from 0 to infinity. We can put we have our 2/3 out there. And then now we have this x minus 3 is going to be this thing we plug in for x. So we're going to do x over 3 to the n. Now if we want to, we can go ahead and clean this up a little bit more to go ahead and kind of, like, you know, get the x kind of off in its own little world and then kind of smush everything else together. So we can go ahead and put that 2/3 back in there. We can go ahead and say we have x to the n over 3 to the n to kind of get the x by itself. And then lastly, we can just go ahead and clean this up and combine that 3 and the 3 to the n to get us n goes from 0 to infinity of 2x to the n over 3 to the n plus 1. And that will be our final answer. Yeah, so like another way we can think about this is almost kind of like a weird version of like a u sub. So like remember how back, you know, whenever we do integrals, how we can go ahead and say, hey, we're going to let this equal u to make it easier to integrate and then plug that function back in for u. This is kind of the same thing. This is essentially kind of like saying if we let x over 3 equal u, and then we're left with 1 over 1 minus u, and then plug that straight in to get us u to the n, and then do x over 3 to the n. It's essentially the same concept as that. All right, so now I have one more example for this type of problem. For this one, we have f of x is equal to x over 2x squared plus 1. All right, so what we need to start doing is we need to go ahead and start kind of, you know, breaking this down to get 1 over 1 minus. I'm just going to just call that like u equals f of x or something along those lines. So now what we can do is we can go ahead, let's first start by factoring out an x just because that's going to be the easiest piece. So we have x times 1 over 2x squared plus 1. So we can see we have our plus 1 right here, which is good, and we have some sort of x, like f of x. We just have to be able to move this around now. So what we can do is we can now move this around and say that we have x times 1 over 1 minus negative 2x squared. So now in our right format to where we have like our 1 over 1 minus a u, where u is like some sort of, I'm going to actually call this g of x since we already established f of x. All right, so now what we can do is we can now go and start plugging this into our series. So now we have x times the series of n from infinity of negative 2x squared to the n. All right, so the next thing, so pretty much from here, all we really have to do is just do a little bit of basic cleanup, just to make this a little bit easier to look at. So we can go ahead. Let's go ahead. We can go ahead. We can move the x back over, and let's separate the 2 and the x squared. So we can say we have x times negative 2 to the n times x squared to the n. We can go ahead and combine this 2 and n to get us 2n, and then throw this x over there as well. And then we can say that we have our series as n goes from 0 to infinity of negative 2 to the n times x to the 2n plus 1. And that is our final answer. All right, so now our next step, so now from here we can go ahead and actually move on a little and take this just one step further. Now that we're dealing with power series, we can actually do something that we actually really haven't been able to do with any other series, which is going to be differentiation and integration. So here we have our other important theorem of the day. And this is essentially just about how to derive and integrate power series. So it says, if the power series of our coefficient times x minus a to the n has a radius of convergence of r is greater than 0, then the function f is defined in the is defined by f of x is equal to c naught plus c1 times x minus a plus c2 times x minus a squared, and so on and so forth. That is equal to the power series n goes from 0 to infinity of c to the n times x minus a to the n. We can say that that function is differentiable, and and continuous if you through that. That is differentiable on the interval a minus r to a plus r. And we can also say that, actually let me switch colors since this is the really important part. F prime of x is equal to c1 plus 2c2 times x minus a plus 3c3 times x minus a squared. And that is equal to the power series n equals 0 to infinity of n times cn times x minus a to the n minus 1. Oh, n minus 1. There we go. So essentially what this is saying is we have just, if we look at this, we have taken the derivative of f prime and so we have f and f prime. So we took the derivative of all of these individual terms and like our partial sum, and we can see how we have that down here. And then we can see how we applied that into our power series. So we're deriving with respect to x, so we can do so if we have like x to the n, we can derive that to get n times x to the n minus 1. And then let me go and switch to another color just so it's not all blending together. We can also do the same thing with integration and say that our integral of f of x dx is equal to c plus c naught times x minus a plus c1 times x minus a squared over 2 plus c2 times x minus a cubed over 3, and so on. We can say that that is equal to c plus our series of n goes to infinity of our coefficient times x minus a to the n plus 1 over n plus 1. So yeah, once again, that's kind of the same thing. You can see how we integrated each of our individual terms, and then we can see how we could also then integrate our series itself. So I'm just going to go ahead and do a quick example of this. So for this one, and just kind of show you, give you a little bit of an idea of how this is going to work. So for this one, we have, we just want to find the power series representation, and we have f of x is equal to the natural log of 5 minus x. All right. So if we want to find a power representation series, there is no possible way that we can do this just as is with our f of x. But we do know that if we derive this function, f prime of x, we can go ahead and take, will be, the derivative of the natural log function, of course, is du over u. So the derivative of 5 minus x is going to be negative 1 over 5 minus x. Now we're in a form to where we can get to 1 over 1 minus x. So now let's go ahead and do that. So we can go ahead and say that we can go ahead and start over here by pulling out a negative 1 times 1 over 5 minus x, and then we can go ahead and pull out 5 from the denominator. Negative 1 times 1 over 5 times 1 minus x over 5. So negative 1/5 times 1 over 1 minus x over 5. we are now in our like 1 over 1 minus x or 1 over 1 minus u, however you want to call that. We're now in our right format to get our power series. So this power series of all of this would get us to -1/5 from 0 to infinity of x over 5 to the n. But we have to remember that this is for f prime of x. And we need f of x. So what we're going to have to do is we actually have to go ahead and integrate both sides in order to get our actual function. So the first things that we want to do is let's go ahead and clean up this function a little bit and separate and get like our x kind of by itself and everything else before we integrate. So we're going to go ahead first. Let's go ahead and put that, let's go and put that 1/5 back in there. We can go and leave the negative out for right now though. Times, and then we're going to go ahead and we're going to split up that x over 5 to give us x to the n over 5 to the n. We can go ahead and move this 5 over here and say that we have negative x to the n over 5 to the n plus 1. So now I can go ahead and integrate that. So we can integrate negative so if we integrate our series, if we go back up, we can look at our theorem and see how it says to integrate. It says we can get, actually we're going to go ahead and just pull negative out in front. There we go. That will get us c plus, remember we have a negative though, series from n goes from 0 to infinity of our c sub n, which in this case is going to be 1 over 5 to the n plus 1, that's our cn, times our x minus a, so which is to the n plus x minus a, which is just x in this point, to the n plus 1, over just an n plus 1. All right, so the last thing we can do is we can go ahead and solve for our c. So whenever we're solving for c, usually a good one to use would be just do f of 0 and let that be your c. So f of 0 is natural log of 5 minus 0, so natural log of 5. So therefore you can say that your final answer is going to be natural log of 5 minus the series of n from 0 to infinity of x to the n plus 1 over n plus 1 times 5 to the n plus 1. All right. Well, that is actually all I have for this afternoon. Once again, like I said, we're working on getting a final exam review before your test, and just good luck on your final this week.